Hello again, ladies and gentlemen. As always, if there's anything you don't understand, please leave a comment below and I'll reply as soon as I can. And if you like this video, please don't hesitate to like and subscribe.
Mechanics.
Alright, so in this video, we will be discussing about some concepts that are relevant to changes in the state of motion. The first concept is the concept of inertia. Inertia is the property of an object that indicates how difficult it is to change the state of motion of that object. As Newton so eloquently explained, an object will remain at rest or move with a constant velocity unless an external and unbalanced force is acting on it. So, why do we need a force? Because objects don't usually like to change their state of motion. They resist any changes, and this resistance is called inertia. When considering linear motion, inertia can be measured by the property that we call mass, which means that objects with higher mass resist more than objects with lower mass. If you wanted to, you could easily verify this experimentally. Imagine that you have a 2 kilogram object and a 1 kilogram object. If the same force acts on both of these objects, let's say about 10 Newton, and now because of the force, the two objects will move, and if you measure the distance that both of these objects move in 1 second, you will see that the 2 kilogram object only moves 2.5 meters, but the 1 kilogram object moves 5 meters. If you want, you can find the velocities at this instance by using the equations of motion, and similarly you can find the accelerations at this moment. Now, acceleration is the rate of change of velocity. So you can see that when the mass is higher, the rate of change of velocity is lower. So we have understood that to change an object's state of motion, we need an external unbalanced force or a resultant force acting on the object. Numerically, we have found that the resultant force in a given direction will be equal to the product of the object's mass and the acceleration. This is usually called Newton's second law of motion. Suppose that we have an object of mass m travelling along a circular path of radius r with an acceleration a. We know that if there is a tangential acceleration a, then there must be an angular acceleration alpha. The tangential acceleration a must be driven by some force F acting on this object, and with time, as the object travels along the circular path, the direction of both the acceleration and the force must change. While F directly causes A, we introduce a new quantity called torque, which represents how effective the force is at causing the angular acceleration alpha. So you can express torque as the product of the force acting on the object and the perpendicular distance to the force from the point of rotation. The force acting on the object is directly proportional to the tangential acceleration, and similarly the torque acting on the object is directly proportional to its angular acceleration. We know that the proportionality constant of the first relationship is the measure of linear inertia, which is the mass m. And following this example, we can determine that the proportionality constant of the second relationship, which is tau proportional to alpha, is the measure of rotational inertia, which is also called the moment of inertia. Now, this next part is purely for purposes of understanding, and you don't need to learn this part to apply equations. So, you can skip ahead using the chapters in the description below if you want, but I do recommend that you stick around because understanding basic concepts can come in handy when you're writing for the exam. We now have the equation tau equals I alpha, but we also know that the torque can be written as force into perpendicular distance. So if we substitute that into this equation, we get the following equation, and we can again substitute F equals ma into this equation to get this. Finally, we can use the circular motion equation A equals R alpha to get this. With some extra simplification, we arrive at the conclusion that for a point object moving along a circular path, the moment of inertia of the object about its rotation axis is I equals mr squared. Now we move on to a compound object, which is a ring composed of multiple point masses arranged along the circular path. If the mass of one of these point objects is dm, where the notation dm is used to denote a very small mass, then the moment of inertia of one point object can be written as dm r squared from the previous equation. To find the moment of inertia of the ring, we must add the moments of inertia of each individual point object. That is, the moment of inertia of the ring I equals all the dm r squareds, which are the individual moments of inertia of the point objects. Now, since r squared is common for each object, we can take r squared out of the summation, which leaves us with I equals sigma dm into r squared. Now, sigma dm is the total mass of the ring because it's actually the sum of masses of each object, which leaves us with I equals mr squared. So you see, the moment of inertia of a ring is the same as the moment of inertia of a point object. Now that we've discussed the fundamentals, let's go over the moments of inertia of some common objects that you will encounter. For each of these, the red line represents the rotation axis. So first we have the disk of radius r, for which the moment of inertia is half mr squared, and we have the sphere of radius r, for which the moment of inertia is 2 over 5 mr squared. Also, for a rod of length L that is rotated about the center, the moment of inertia can be written as 1 over 12 ml squared. Whereas if the rod is rotated about its end as shown, then the moment of inertia increases to 1 over 3 ml squared. Now, if you compare these objects, you will see that the moment of inertia can commonly be written as some constant times mr squared or ml squared, depending on the kind of object. So we can write a general equation for moment of inertia as I equals kmr squared, where k can be any constant. Now this k is referred to as the radius of gyration. For a disk, the radius of gyration is half. For a sphere, the radius of gyration is 2 over 5. Alright guys, so that's it for this video, but I hope to see you soon with a video on angular motion. If you hover over my YouTube channel picture, you will get an option to subscribe, and if you like this video, please hit the like button and leave any possible feedback in the comment section below. Thank you. Peace out.